we get started.
Okay. Hi. Can you hear us properly?
Yes, we can.
Okay,
I'll give an introduction very briefly. Your talk is entitled Magnetic Levitation by Rotation, and will actually be given by the two of you. So this looks very exciting. Thank you so much.
Yeah. Hi, I'm Joachim, and this is Frederik, and we want to talk about recent work on this newly discovered type of magnetic levitation. And our work, we've already gotten it accepted in Physical Review Applied, and we expect the paper to come out within the next few days. So first of all, the phenomena is quite simple to create. All you need is two magnets, one that you spin very rapidly, and once you approach that rotating magnet near a free magnet, you will see that the free magnet locks on to a specific point and will levitate as you move it around. We've then investigated this more thoroughly with a setup with better quality control and better speed control. And here we see that the rotor magnet is attached to the motor with the north and south perpendicular to the rotation axis. And when you then place a floater magnet or free magnet underneath, it will find its equilibrium quite quickly. Here in the video, you also see this aluminum plate we have underneath, and this is to create eddy current damping in the free magnet that causes the oscillations to stabilize and thereby making the initial conditions more consistent. Using these experiments, here we have painted the north poles of both the rotor and the floater magnet. We see that the floater magnet orientates almost vertically, precessing synchronized with the rotor magnet. We've then also done some simulations, where this one we started from rest, and here it finds its equilibrium point quite quickly and precesses in the same way that our experiments show. Now to the modeling.
Yes, so for the next part of the talk, we will try to explain why this phenomenon occurs, why this levitating state and this exotic moment configuration is stable. So in our model, we have a dipole magnetic field from the rotor acting on the floater. We have drag, which we model as proportional to the linear and angular velocity. And then we have gravity. And because the dipole field decreases with distance, it has a gradient, so it produces both a force and a torque that tries to align the floater moment with the dipole field. Putting these into Newton's second law for translation and rotation, we get these equations that we can time step integrate to get the full time evolution, as you saw in the last video. And it turns out that it is extremely important that the rotor magnet is somewhat shifted relative to its rotation axis or has its moment tilted. Because then, besides a rotating horizontal field, there is a vertical static component of the dipole field at the floater. And only then do we get this counterintuitive configuration with the moments north-north and the floater almost vertical with some angle theta. Now I will go through the torque and force balance in steady state. So it seems at first that this dipole torque is unbalanced, so the moment should flip over. But it is in fact counteracted by the rotation itself. In our simulations, we get this state of rotation where the floater moment precesses at the same frequency that the rotor is rotating, omega r. But it has a second rotational mode around the moment itself. This is analogous to a spinning top, where you also have spinning around one axis and precession of that rotation axis around vertical. And just like the spinning top can stay upright against gravity, the rotation allows the floater to resist this magnetostatic torque. In fact, when we analyze the system in the rest frame of the rotor, then the magnetic field and the dipole torque are constant, but we get this fictional gyroscopic torque from the rotation and inertia of the floater. So that's the explains the orientation of the moments. To explain the levitation itself, we need an attractive force and a repulsive force. The attraction comes from the vertical components of the dipole field and the floater moment, while the repulsion comes from the horizontal component, because the horizontal components are anti-parallel and so lead to repulsion instead of attraction. There also is the effect of gravity, but this is a small and unnecessary correction. The phenomenon is fundamentally magnetic. Okay, now why does this happen from rest and why is it stable? Well, because of this balance between the gyroscopic torque and the magnetostatic torque, the steady state orientation of the floater will be a function of distance. It will be more horizontal when the magnets are close to each other and more vertical when they are far away. And this means that the repulsive and the attractive force scale differently with distance. It is more repulsive at short range and relatively more attractive at long range. And in between is an equilibrium point. And also, a displacement in either direction leads to a restoring force, which is why it is stable. Indeed, when we do simulations with the center of the floater fixed in space, so we just look at the rotation, we can get force curve like this, the average force in steady state versus distance. And in some cases, it crosses from positive, so attractive, to repulsive, so negative, so repulsive, as the distance decreases, which corresponds to a stable equilibrium point. This explanation does not require gravity at all, which is why the phenomenon works in all directions. And when we reach steady state in the simulations, then turn off damping, it remains stable. Damping makes it easier to reach from rest, but it is not strictly required. All we need is the magnetic interaction and gyroscopic stability from the rotation and inertia of the floater.
So up to now, we've only looked at neodymium iron boron magnets and of one particular size and magnetization. So we've conducted experiments where we vary the magnetization while keeping the size constant. And we've also done vice versa, changing this size of the magnet, keeping the magnetization constant. And here in this graph, we see the minimum speed of which the rotor has to rotate for levitation to occur. And here we can see as the magnets become larger, they have more inertia and thereby can levitate at lower speeds than the result than the smaller magnets, where magnetization doesn't really affect the minimum speed required for levitation. On the other hand, if you look at what distance away the levitation happens, when you have a larger magnet, they tend to levitate closer to each other, where a stronger magnetic or a resonance would cause the magnets to levitate further away.
Now, to compare theory and experiment, we needed to do simulations with many parameter values, but only some of these lead to stable levitation. So we fixed the position of the floater just looking at the rotational dynamics, and then we get this plot of dynamical phases. At low frequencies and small distances, the moments are anti-parallel in steady state, as we expect in the static case just from the magnetostatic energy. In the blue phase, we get the configuration that we observe experimentally when they levitate, with the north-north alignment and the floater pointing nearly vertical. In between, in the green phase, the motion is more complicated with the theta angle, the floater polar angle, varying in time. But only in the blue phase do we get these force curves that change sign with distance. Some of these force curves are consistently negative, which means that the attractive force never exceeds gravity. In other cases, they only cross the x-axis once, which means that the magnets collide before they reach the equilibrium point. But there are some experimentally relevant parameter values where it crosses from positive to negative with decreasing distance. They are marked by orange crosses, and these are the predicted equilibrium points. We can compare this to our experimental data. So we have the same X and Y axis, rotor speed versus levitation distance. And we see the same general trend. Increasing the rotor speed decreases the equilibrium distance. But the experimental data is in a somewhat broader frequency band and slightly lower frequencies, which suggests that there's still room for quantitative improvement in the parameter determination and the theoretical model itself.
Now on to something that the model also cannot really predict. And this is the different modes that the phenomena can have. And so let's say we keep this magnet constant with the same size, and we just change the rotor speed. What happens is then at low speeds, no modes will occur and it will just float. But then once you hit a resonance at a bit higher speeds, you start to see this up-down mode appearing. And then at even higher, you will start to see this side mode, which we've also seen in simulations. And then at even higher frequencies, we see this mixed mode between this up-down mode and side mode. And then at even higher frequencies, a floater magnet has moved close enough to the rotor magnet that the magnetic field changes quite dramatically during its oscillations, leading to a U-shaped mode. So in conclusion, the phenomena is easy to create. All you need is a spinning tool and 2 magnets. And it doesn't require gravity, meaning that you can move the magnets in any orientation and contextlessly in 3D. Just to sum up the theory, there's a rotation counter. The magnetostatic torque is counteracted by the rotation torque from the gyroscopic precession. And for further improvements, we need eddy currents and instabilities to maybe get these up-down modes in our simulations. And we would like some more quantitative theory for predicting the curves and the parameter dependence. Thank you. And it's time for questions.
Wow, this is really very cool. Thanks so much for showing us this. I think we have time for one quick question. If anybody would like to raise their hand. Otherwise, maybe I can ask one quick question. How on earth did you figure this out? Well, what inspired you to start spinning a magnet on top of another magnet, like you show in the clip here? I mean,
so
really
our
neat.
paper is not the first one in the field. It's actually the second one. The first paper was written by someone who discovered it in their backyard as an aerospace engineer. And magically, we stumbled upon this paper. And then we tried reproducing it ourselves and got shocked when we saw it actually worked. Yeah.
Yeah. I think
Thank you so much. Yes, they want to go test it out in the lab now. So
yeah.
Yes. All right. Well, thank you. I look forward to going and reading this paper. We will now move to our next speaker. This is Somnath, and I believe they are here.